There we go. Perfect. No matter how many times I do this, every single time it's like, how does a computer work? Right, so we're gonna get started with today's talk. First of all, thank you very much for coming today. We know it's week 7, so there's lots of deadlines and problem sheets going around, so it really means a lot to us that you're here tonight. And it's also British Science Week, so we're really glad that we can have an event this week. In addition to that, I actually gave this exact same talk yesterday to 10 or 11 year 10 students for British Science Week as a kind of like backup activity, because we wanted to do some solar observing, but we all know how the weather was yesterday. So that plan went down the drain. So we're gonna get started on the talk along the way. If you have any questions, just shout them out. It's only like 5 or 6 of us. No, wait, how many is it? We're 7, 8, counting me. So we're a good number of people. So just shout it out if you have any questions. And yeah, we will get started. Committee, take pictures. Yeah. This is me bossing them around. Right, so we're gonna get started on the talk, which is called, oh, sorry, I'll just readjust the laptop because I'm gonna be talking that way. Yeah, which is Bouncy Stars and Life as We Know It. This talk is basically centered around a lot of my highlights of semester 2. So I'm gonna be sharing some parts of like physics that I've worked on that's basically my group studies project and my favorite module from this semester as well. So off we go. Right, so first activity, if you could please go to slido.com and enter the code 677626, and there should be a word cloud poll activity there for you to participate in. So the question is going to be, how do you define life? So I'm gonna give like a minute or 2 for that, and then we're going to see what the word cloud says. Is everyone able to access it? Yeah, perfect. Sorry? Is it visible? Just give me a second. Okay, it should work now. Yeah. No problem. Yeah, you're gonna see that as people answer, I guess. You can see the other questions as well, but.
Do you mean biological life, or do you mean like living?
Just life. Just life. What is life? Isn't that what we're all here to find out? That is the goal of the talk today, guys. I'm going to tell you what life is. Okay, I have 0 answers so far. Ooh, 3.
Why did you immediately look at me?
I don't know. It was literally like, that's something Oscar would say.
Well,
Right, we have some really nice answers. Things that are living, breathing, happiness, tiring. As a university student, I think we can all relate. Consciousness, perception. Hard, yeah. Feel free to give more than one answer also, so that's also fine. Right, so if I was to kind of summarize everything that we have in here, so I'm just gonna do the screenshot so we can see it in the presentation. There we go. Right, so if we were to summarize, or if I was to summarize all of these things in here into one kind of broad bubble, it would be that the idea of life has to do with consciousness, the ability to take in information, process it, and then react to it. That's how life as we know works. Like human beings, we we have our senses, we interact, and we respond to things. Plants, they respond to changes around them as well. If it's sunny, you have better, healthy plants. If it's not, then you have winter and all the leaves fall out. But the gist of it is consciousness and the ability to respond to stimuli. So the name of this talk is Bouncy Stars and Life as We Know It. So before I delve into it, I thought I'd share a brief history of this talk. So effectively, I think, semester 2. So this is my 3rd year. I'm doing physics with particle physics and cosmology. One of my modules is asteroseismology and exoplanets. Just as a guess out there, does anyone have any ideas that come to your mind when you hear the word asteroseismology? How about if you hear the word seismology? Earthquakes. So earthquakes are basically to do with the internal motion of the Earth. So subsurface motion, how that manifests on the surface of the Earth. Asteroseismology, as you can guess, is exactly the same, but with stars. So it's about studying the inner structure of stars and how that manifests on the surface of stars. So that's basically the module asteroseismology. In a nutshell, that's what we study. But I enjoyed this module so much, and I was so glad that I managed to get a group studies project in this exact same field, which is basically helping the upcoming ESA Plato mission, which is going to be launched sometime in the 2030s, I believe. And the goal of that particular mission is to observe stars, which are potentially hosts of exoplanets which have life, and to even study the asteroseismology of these stars. So basically how they oscillate, how you can study their surface structures, the processes going on within the surface, and so forth. So this diagram that you see here is an artist's representation of what Plato would look like in outer space. And the final chunk is basically the grand question that pretty much all of my Google News feeds tend to show, which is exoplanets, habitable zone, is there life out there? Pretty much every sci-fi movie I have seen that has the theme of astronomy is about, life or aliens or the idea of having some kind of astrobiology. So we're going to kind of blend all of these three things and see how they tie together. Right, so in this slide, the first animation that you see is something that at some point we've all probably seen either in labs or just playing around with toys. So if we were to have a giant slinky, and let's say Rodri was standing at the end of the lecture theater at that end, and I was holding one end of the slinky and Rodri was holding the other end, and if we were to shake the slinky, we would observe a pattern that was somewhat like this, except it would be still at both the ends. Eventually, we would have standing waves forming because that is how energy is trapped within a string. Does that sound familiar? Have you tried that either with strings or guitar string or a slinky even, or even sound waves, like when you have if you're a physics student, please raise your hand. Excellent. Have you done the resonance tube experiment in year 1 labs? Yeah. Basically that. In 2 dimensions, it looks like that, as we all know. In 3 dimensions, we can replicate the exact same thing. So in 2D, we have standing waves on a string. And in 3 dimensions, the analog of that would be spherical harmonics. So you get spherical harmonics, which are effectively standing waves set up on the surface of the sphere. And that's how energy is stored. And when we say stars oscillate, what we're basically saying is that energy is trapped within the star such that it makes the star bounce, hence the name bouncy stars. So let's see how this ties in with the next bit, where we're going to learn about why stars bounce in the first place. So this animation that you see right here is basically a cross-section of a star. In the center, we have the core, and then we have the radiative, convective zone, and we have the outer layer, which is the photosphere. This is not to scale, so in a real star, this is not exactly how each of the layers are spread out, but you get the order of it. So within a star, we know that the core is the hottest layer of the star. So you have the core right here. And the best way to think of this is, let's take a step back, go back to our GCSE physics class, and you have a beaker of hot water, and you add a drop of food dye into it, or like any kind of coloring into it. You place that on a Bunsen burner. What happens to it? Just, you can shout it out.
This one means something you did.
What? No. Okay, cool. Yeah, exactly.
Oh.
See, it's not something that I just did. So
I didn't do that though.
yeah, so if you have, so let's say you have some boiling water, and if you were to like drop a drop of food coloring into it, then first, of course, it would sink, but then as it sunk, it heats up and it rises, and then it sinks again. So you have a kind of temperature gradient that's set up within the beaker. So it's hotter towards the bottom and cooler towards the top. In a star, because it's basically gas, so you can kind of take that approximation. You have high temperature down here, so there's a pressure gradient that's developed as well. So if the temperature changes, as we know from the ideal gas law, you need to have the pressure changing as well. So this gradient in pressure and the rising and falling gas, and of course there's gravity as well, that causes sound waves, so the vibrating motion of the molecules of the hot gas within the star, to cause standing waves within the star. And you can get standing waves of various different types. So the first type that you see is this that goes up and down. That is what we call a radial. Radial meaning you can literally just, the star shrinks and expands, and that is your radial mode standing wave. That goes all the way through the core. And then you have some higher, what we call higher angular degree oscillations, in which effectively you get the waves that go all the way down, hit a particular layer, and then they curve away, because when you have a pressure difference, waves are basically, they curve around that region. So the pattern of these oscillations that we observe, they can give us information about the layers that they reach up to. So for instance, this particular mode, if we were to observe it, that would give us information about this layer of the star. Similarly, next mode, this mode that we observed, that would give us information about that first layer of the star. And we can observe this very, very closely with our sun, but when it comes to observing other distant stars, we can only observe like the very simple patterns, because what we get, because they're very far off, we only get a disk average signal. So you can just tell whether it's, expanding, contracting, or overall is one side moving towards us or away from us. So essentially, that's how we find out about the inner structures of the star. So where the different layers are and how they're distributed. So when we actually go on to observe this, what we see is something that looks like this animation with the blue and red stripes over here. So if you just ignore this graph towards the bottom, I just wanted the animation up top. So what we see is blue and red regions where, as the star oscillates, the blue regions are the regions that are moving towards us. So that light is blue shifting, and we know that blue shift corresponds to something moving towards. And the red segments that you see, that is regions that are red shifted, so they're moving away from us, they're moving further away from us. And that pattern keeps repeating itself around the star. So that's how we find out what exactly the pattern of oscillation that we see in this graph is on essentially the spectrum that we observe. And this is a very powerful tool because it can give us information on the mass, on the rotation period of the star, the evolutionary phase, so whether it's, let's say, a young dwarf star or if it's a red giant star, and even about the composition, because as we know, pressure and temperature, they tend to vary, and the density varies depending on the composition. So if something is more hydrogen or helium dominated, it will have a different kind of oscillation spectrum compared to something that's, a more heavy star in a later stage, like a red giant, which is more lithium and, heavier element dominated. Any questions along the way? Anything? Cool. So that was the first part of the title, Bouncy Stars. Next, we're going to learn about a bit more about where it is that we could potentially find life and how that links to life as we know it. And the key to this is exoplanets. So exoplanets effectively are planets, or just, planets, orbiting stars other than the sun outside the solar system. So they could be orbiting other stars, or they could even be interstellar planets that are, just going through space. They don't really have a host star. That could be a very lonely planet. They exist. Hello. No problem. So since we think that life could potentially exist on exoplanets, the key to this is to first answer the question, how do we detect exoplanets? One of the most common methods that has been used by the satellite Kepler in the past and will be used by Plato in the upcoming missions is the transit method. So in this animation right here, we see a star as we view it from Earth, and you have a planet. Now, the planet, as it passes in front of the star, it blocks some of the light that we receive from the star. And that results in this dip that we see. So when the planet is not eclipsing the star, we get something like that, and then a little dip. It is this dip that we can observe using satellites and telescopes, and even ground-based telescopes. They're very, very powerful. And as a result of that, we can effectively measure the periodicity of the planet. So we can get information about the orbital period of the planet. We can even get some information about the size of the planet. And we can effectively determine a lot more, such as information about the atmosphere of the planet and so forth, but we're going to get to that in a bit. So this ties in with a key concept of physics called flux, which is effectively the amount of energy you receive. So the light energy or the power that you receive. And that very quantity reduces when the planet passes over. It's exactly the same concept as a solar eclipse when the moon passes between the Earth and the sun, and it blocks the light from the sun. That's exactly the case, but here instead of a solar eclipse, you have this planet eclipsing the star for a temporary period of time. The next most common method is the radial velocity, or the Doppler method. Now, as we know from just general physics concepts, the idea of center of mass is key to stability around any system. So if we had a really, like a high table or something, or if we take that chair, for instance, and if we put like a 10-kilo mass on it, like not even 10 kilo, let's say 100 kilo mass on it, it's a super strong chair. And if we were to just give it a slight nudge from the top, it's very likely that the chair will fall over because the center of mass would be fairly high up. It would not be close to the ground, so it would be highly unstable. Whereas if we were to add if we were to add the 100-kilo mass to the lower level, like maybe let's say close to the bottom of the chair, then the center of mass would be very low and the chair would be quite stable. Does that make intuitive sense? It's pretty much exactly the same concept at play right here. So when we have a star and we have a planet going on an orbit around it, the planet doesn't necessarily orbit around the star exactly. Instead, the star and the planet, you can think of them as kind of fusing together in a way, such that they orbit the common center of mass in between the two bodies. So you have the star going in a circle around that common center of mass, which is right above there somewhere, and the planet orbits that as well. What this means is that the star is not stationary, as we might have expected. And if that is the case, at some points in time, the star is moving towards us, and at other times, the star is moving away from us. Now, if we think back to what we talked about a slide or two ago, if something is moving towards us, we detect a blue shift if something is moving away from us. That same thing appears to be redshifted. And it is that redshift or blue shift that we can easily detect in the spectra that we receive from the stars. So depending on how the star wobbles around this common center of mass, we can determine exactly how many planets it might have, where these planets could be, and even how large or how massive these planets are. And that is a very powerful method of observing and detecting exoplanets. So effectively, redshift and blue shift, just to summarize it, it's like ambulance sirens. So if you have an ambulance with a siren moving towards you, the pitch gets higher. If it's moving away from you, it keeps getting dimmer and deeper again. Right. So now we're going to move on to the third part of life as we know it. So what makes a region habitable? And the answer to that, as per our current understanding, our limited understanding of life as we see it on Earth, if we were to extrapolate that, the habitable zone is effectively a region around the star where standing bodies of water could exist on the surface of a rocky planet. Does that ring any bells? Earth, precisely. So basically that's saying that in order to have life in the universe elsewhere, we need to look for another Earth. Personally, I think that's debatable. We have very limited understanding of exactly how the universe works. What if there's life out there that's not the way we know it to be? But science and research papers, if you were to read it, like I found this in a research paper that I was reading for my project, and this is how they define life. So we have accepted that, and we are going to go ahead with this very understanding. But that raises the question, why water? Does anyone want to contribute any ideas? Why is water important to life, apart from dehydration? Just feel free to shout it out.
Because we have a liquid medium, so obviously different chemicals can react together.
Yeah, that's a very good reason. Yes. Precisely, it's a very, very good solvent. So that's exactly the next point. So most substances, as we know, it's like minerals, as the two of you mentioned, they're soluble in water, and you need a medium for chemical reactions to occur, and water is the perfect medium for that. So the longer that the habitable zone lasts, so the longer that the temperature in that region is ideal for water to exist on the surface, the longer you have for complex life to develop. So one of the reasons why Earth has been able to develop complex life forms as we know it is because it was in such a region that water has been able to exist for a couple of billion years. And that means that that's sufficient time for, to go from single-celled organisms to humans and whales and plants as we know them. Right, so now we're going to have the second Slido quiz again. So if you could just go on to slido.com on your phones and type in the code 677626. I will type it in the chat. I just realized that I forgot to run the, I do not know what that's doing. There we go. Can you see the question yet? Okay, perfect. I will, as soon as this loads. There we go. So the question is, which compound or compounds is a signature for biological processes on exoplanets? So feel free to select the option that you think would be suitable, and we're going to have a discussion in a bit, in a minute or two. So your options are oxygen, carbon dioxide, nitrogen, methane, ammonia, water, ozone, or all of the above. Don't let the answers influence you, but go for it, whichever one you think. So we've got 2 answers so far. 3, that's looking better. Yeah, oxygen. I think we've got 4. Trying to figure out if that's everyone. Oh, we've got 5. Yes, I think that's everyone. So I'm just gonna screenshot this so we can see it in the talk, and I'm gonna close that. There we go. So the answers are pretty much exactly how I expected them to go. So we have 20% have suggested oxygen and 18% have suggested all of the above. Every single answer on there is correct. So technically everyone is correct. All of these compounds that you see, these are really strong signatures of biological processes occurring on the planet. And we are going to find out exactly how we know that these gases exist shortly. There we go. I don't know why it's not changing. Come on. Right. So we're going to find out in a bit how we find out what the gases are and how we find out like the methods for detecting these gases on exoplanets, since they are quite distant. Now, this table that you see in front of you, this is from a research paper and how they categorize the different habitable zones that we have within our solar system. Now, this is for an Earth-sized planet orbiting the sun, and they have categorized it into 5 different kinds of planets. So there's, I just love the names. We have a moist greenhouse, which is about 1 astronomical unit from the sun. So that's the same distance as the Earth from the sun. And then you have a runaway greenhouse, which is just about, it's starting to get really warm. And then you have a recent Venus, which is typically a Venus-like planet, so at a Venus-like distance, so that's 0.75 AU. You have maximum greenhouse, so that's just before you hit the really cold region where you have Mars. And then you have early Mars, which is basically where Mars is at, potentially a couple of million years before its current stage of evolution. And the fact that you can see that there's quite a bit of discrepancies between the 2 values, in the sense that you can see that this is a 1993 paper, this is a 2013 paper. You have about 20 years, and that just shows you that exoplanets are a field that's that's varying and developing very rapidly. The fact that you can have almost this is pretty good, that's exactly the same, that's exactly the same, but then these 2 values show you that this field is evolving very fast, so you're in for surprises. Right, so now we're going to answer the question on how we find out what these exoplanet atmospheres are and how we can detect them. The key to this is to observe transits, so planets eclipsing their host stars. And the way that scientists or exoplanetologists and astronomers do this is that they treat the planet's atmosphere as a filter. So think of it as the starlight as it passes through the thin film that is the planet's atmosphere. It gets partially blocked and some of it goes through the atmosphere, and that behaves as a filter that only lets certain wavelengths through, and we can detect this on the spectrum that we receive because we know what the starlight should look like before it has the transit, so we know exactly what the star spectrum looks like. And then if you get a change in the spectrum, you can see that signature of the planet's atmosphere imprinted on that very spectrum that you receive. And once you measure this, you can get information on what compounds are in the atmosphere. So all the compounds that we saw previously, like oxygen, methane, carbon dioxide, all of that are very strong biosignatures of potentially having biological processes as we know it occurring on the planet. Additionally, you can have clouds and hazes that would impact that. So for instance, if you have a planet with a very thick atmosphere, very little starlight will get through that. So you have a very thin or a very weak filter effect occurring. At the same time, if you have something that's very, very bright, a lot of that is going to get reflected. So you get kind of an even brighter like blur around the star. So that around the planet, sorry. So that also gives you quite a bit of information. And one thing that I found really intriguing is that there's two types of gases that they classify this. Unfortunately, I do not know why they're called type 1 and type 3. I have no idea what happened to type 2 gases, but we're going to find out what type 1 and type 3 gases do. So type 1 gases are gases that are produced from metabolic reactions. So like reactions that are undergone by life forms, like for instance, plants and animals. So animals, as we know, breathe in oxygen, remove carbon dioxide. Plants do the exact opposite. Those would be byproduct gases, for instance. However, there's a very high chance of error with this because geography, so geology and biology, a lot of the molecules are very, very similar. So for instance, we know that certain rocks can release gases as they erode and decompose. Those gases are the exact same as the gases that are released when there's human processes as well. So that's something to be on the lookout for. So type 3 gases are chemicals that are produced that do not correspond to life formation. And these gases are distinct as well, so you can make out the difference between biological metabolic gases and non-metabolic gases. And those are, broadly speaking, the two categories of gases that they have. And these are effectively produced for organism-specific reactions. So the way that I understand this is that these are more likely to be produced in processes before the organism can undergo metabolism. So like the very ingredients of forming that organism itself rather than a process that the organism does in order to sustain itself. So as we discussed previously, flux is effectively the amount of light that is received by the planet. So we live on Earth, we have the sun, we know exactly how much light and heat we get from the sun, and that helps us sustain life on Earth as we know it. It maintains water as a liquid on the surface. So what we have decided as astronomers is that if there's a planet, an exoplanet, which has the exact same amount, or sorry, exact same proportion of starlight and heat that it receives from its host star, then it too must be in the habitable zone, and it should also be able to sustain liquid water and life on itself, on its surface. And that is how scientists currently define the habitable zone. Can it sustain liquid water on its surface? Does it get the same amount of starlight as Earth does? If so, then yeah. And this brings us very close to the end of the talk. And this is actually one of my favorite slides while I was making the presentation. So broadly, again, this slide shows 4 different categories of planets out there. So we have, first over here, we have hot Jupiter. Again, these are all artist depictions. These are not what they really look like. We don't quite know what they look like. So this is a hot Jupiter, as you can guess from the name. It's very hot because it's very close to its host star. And it's about the same size as Jupiter. That's why it's called hot Jupiters. And then you have these sub-Neptunes, which are effectively stars which are planets which are much larger than Earth, but just smaller than Neptune. And then there's this category, which I'm going to ask you to guess the middle of it. Like I'm not expecting anyone to know the answer. It's more just because I want to have fun. And then you have super Earths, which are one of the most popular contenders out there for potential life hosts. This is a category of planets that I learned about, I think on Tuesday or last week on Thursday. Yeah, I think it was Thursday probably, in my first ever exoplanets lecture. And for a second, I thought it was a type of Cheetos, and I thought that the professor was pulling a prank on me. Does anyone want to take a random guess about what these planets might be? They're very light and they're very large. Just feel free to shout out stuff. Very light, very large. Cool. I shall scroll over to the next thing so you can see what it is. They're called super puffs. That's so close. So this category of planets is actually called super puffs. So I'm going to tell you a little bit more about each of these categories. So super puffs, they have masses that are just a few times that of the Earth, but their radii are much larger than that of Neptune. So imagine something which is massive, but in terms of size, but in terms of mass, very, very small. So Saturn, if you think of it, it has a density less than that of liquid water. So if we had an ocean that was large enough to hold Saturn, Saturn would probably float on it. It's so light. And that's something that's very cool. And super puffs are relatively new, so we haven't found very many of them. The next category is hot Jupiters, but because they're very, very close to their host stars, effectively, some of them don't even have like a solid surface. Some of them have a molten metal surface. So they're very, very exciting planets to study. And sub-Neptunes, again, as we mentioned, they're planets with radii smaller than Neptune. And lastly, super Earths, which are the most exciting and potential planet hosting, life hosting planets, not planet hosting stars, life hosting planets. They're up to 10 Earth masses, and effectively most of them they're like probably the most popular kind of planets out there in other star systems. And it's really astonishing that in the solar system we don't have a single planet that fits the super Earth category, but pretty much every star system that we've seen out there that has planets almost guaranteed to have a super Earth of some sort. So it's a real coincidence that we don't have one in the solar system. Even more interesting is about 85% of the stars out there, they're binaries. So they're binary stars, so you have two stars orbiting each other. Our sun is a loner again. So, I mean, sometimes, although astronomers say, the sun is just another star, then you have planets everywhere. I like to think that the solar system is actually kind of special. It's not a binary star. We don't have a super Earth, so that really does make us stand out. And that brings me to the final thing, which is a final Slido quiz. So once again, if you can just go to slido.com and type in the code 677626, and I will activate the final quiz right here. So the question is, which planet type could host life? And this is just kind of to just consolidate everything from the talk today. So feel free to give your votes in. We've had 3 votes in, 4. I'll just give it a couple more seconds. Just wait until it's 45. Sorry? Sorry? Oh, okay, perfect. No problem. So that is all the answers that we have, and I shall just take it there. Perfect. So which type of planet could host life? And indeed, we think, as per our current understanding, super Earths are the most likely candidates to host life. So well done, you've all been paying attention. And super puffs, most likely not, because they do not have a solid surface. And the definition for a life-hosting planet is a rocky surface. Hot Jupiter's way too hot. You can't have water on the surface. It would evaporate, so can't have water. Sub-Neptune's the most popular argument out there is that it would probably be a bit too cold for water to exist as a liquid on the surface. However, there's not really much evidence on exactly why sub-Neptunes might or might not be life hosts, but super Earths are pretty much in every scientific article that you see on your Google News bulletin about life may have been discovered on a planet outside the solar system. It's probably a super Earth. So that brings me to the end of the talk. And if you have any questions, I would be more than happy to answer them. With that being said, I will stop the recording.